In this section, we'll demonstrate how to run Mali offline compiler on a fragment or vertex shader program to generate a report showing the expected performance of that shader on a Mali GPU. Mali offline compiler is a static analysis tool, so there's no need to connect to a device. You can run reports on any of the Mali GPUs, which can help you predict the expected performance on devices you don't have access to. You need to run Mali offline compiler from a command line. Here is the fragment shader program, which is responsible for the dissolve effect that occurs in our game when the enemy soldiers die. The command to run Mali offline compiler is simple. You just need to specify the Mali offline compiler command, your shader program, and the GPU that you want to analyse the shader against. Here I've chosen the Mali G72, a popular Bifrost GPU available in many mass-market devices. The first part of the report gives information about the shader and the configuration of the run. We see the GPU and its architecture, the Mali driver version, and the type of shader analysed. We can see that the shader uses 64 work registers. This is the maximum number available in this GPU. The available physical register pool is divided among the shader threads that are executing, so reducing work register usage can increase the number of threads that can be executed simultaneously, helping to keep the GPU busy. To reduce work register usage, try reducing precision from high P, 32-bit, to medium P, 16-bit. This enables the GPU to store twice as many variables per register. For Valhalla and Bifrost GPUs, we can see whether any variables are spilled to stack memory, and if so, how many bytes per thread are spilled. Shaders that spill to stack are expensive for a GPU to process, so if you see stack spilling going on, try to reduce register pressure by reducing variable precision, reducing the live ranges of variables, or by simplifying the shader program. Here you can see the percentage of arithmetic operations that are performed at 16-bit precision or lower. A higher number here is better, because 16-bit precision, selected with medium P, is twice as fast as high P at 32-bit precision. We can see that only 2% of arithmetic computation is done at 16-bit precision. This means that the shader is using 32-bit precision, high P, for most of its calculations. The shader will operate more efficiently if we reduce precision from high P to medium P. This reduces both energy consumption and register pressure and can double the performance. There are situations where high P is always required, such as for position and depth calculations, but in many cases there is little noticeable difference on screen when reducing precision to medium P. Next, there is an approximate cycle cost breakdown for the major functional units in the Mali shader core: the arithmetic unit, the load store unit, the varying unit, and the texture unit. The unit with the highest cycle cost in either or both of the shortest path cycles and longest path cycles is a good candidate to optimise. Here we can see that the arithmetic unit is the most heavily used. We can optimise it by reducing the number of mathematical operations that it performs, or the precision of those calculations. For Valhalla-based GPUs, such as the Mali G78, arithmetic cost is shown broken down by FMA, CVT, and SFU pipelines. All Valhalla GPUs implement two parallel processing engines, each containing their own set of arithmetic pipelines. The data presented in the report is normalised based on the number of engines in the design to give an overall cost for the targeted shader core, not just for a single engine. The shader properties section gives information about the shader's use of language features that can impact the performance of shader execution. We can see that this shader contains uniform computation. This kind of computation will produce the same answer for every thread in the draw call or compute dispatch. The Mali driver can optimise this away, but it still has a cost, so you should move this kind of computation out of the shader code and onto the CPU to be executed at draw time. This tells us that the shader can modify the fragment coverage mask. The fragment coverage mask determines which sample points in each pixel are covered by a fragment, using the discard statement to drop fragments that are below an alpha threshold. Shaders with modifiable coverage must use a late ZS update, which can reduce efficiency of early ZS testing and fragment scheduling for later fragments at the same coordinate. You should minimise the use of discard statements and alpha to coverage in fragment shaders where possible. Fortunately, this shader does not force a late ZS test, which would completely disable early ZS testing and hidden surface removal, a significant efficiency loss. You can export this report to a file by running the command with this extra command line option. If you are working within a continuous integration environment, you can also export Mali offline compiler reports as machine-readable JSON files, so that you can build your own dashboard to monitor shader performance over time. Sample reports and JSON schema definitions are provided in the installation directory. Check the help page to see a list of all the available options. In the next section, we'll look at the developer resources available to help you design more performant content for mobile and to help you get started with ARM Mobile Studio tools.